Relation. Well, what do you think? What's the name of the chapter? Relations and functions. What's a function? Does it pass the vertical line test? Does this pass the vertical line test? Actually, you can argue it doesn't, but we're calling it a function. Actually, that's kind of weird. I never thought about that before. A function is a relation, okay? A relation isn't necessarily a function, right? Remember, that's a relation between x and y. That's fine, but it's not a function. It doesn't pass the vertical line test, okay? This one does. I know it doesn't look like it here, but I'll explain when we get there. Okay, the Carter family are driving to the Yukon for a vacation in the Yukon. Poor them. I could think of better places I'd want to go, but who knows, maybe it's summer. This graph represents the amount of fuel in liters, okay, of their car, which of course is kept in the gas tank, okay? This is time. Is that on the right axis? Does that make sense? Is time always continuous? Is it always independent? It's always on the x-axis, 99.9% of the time, okay? All right, so some of us already know what's going on with this picture? It tells a story. Think, this is fuel in the tank in liters. Here's 0700 hours, or 7 o'clock in the morning. This says at 7 o'clock I got 50 liters in the tank. And a linear relationship occurs to get to B. How many liters do I have at point B? 20. How would you say that in language that people would understand? I drove a certain amount of time. I burned gas. That's what happens when you drive. And you could be more specific. How much gas did I burn? Looks like about 30 liters. How long did it take me to burn that 30 liters? Well, whatever time this is, okay, let's figure out the scale. There's 12 o'clock. If they were nice, this would go up in nice increments of maybe an hour. Does it? There's 1, 2, 3, 4, 5 between 12 and 7. Yeah, that looks like it actually makes sense. 12, do you want to go, well, this is 1700. That's also known as 5 o'clock, right? Okay, are we familiar with 24-hour time? Okay, some of us are, some of us aren't. That's 1300, or 1 o'clock, right? 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock. Okay, and then they're done driving. Well, you know you can't drive forever. You don't want this to happen, do you? What does that mean? You ran out of gas. Not good. I got 0 liters in the tank. You never want that to happen. So do we understand what's going on here? Sure. You filled up, right? The gas tank went from 20, up to 60. I don't know if it's full. Maybe it holds more than 60 liters, but they put in up to 60 liters. Now, let's think. Remember I said how this has to be a function? Could this possibly be a vertical line? Whatever time this is, can you instantly fill up your tank? Like in a billionth of a second? You can't. It takes time, which means time is passing as we go from here to here. This is not a vertical line. If I exaggerate it, that has got to look like that, and that does pass the vertical line test, right? Okay, it has to be slanted. Time cannot stand still as you fill a tank or do anything, right? Time is continuous. Maybe it took only 5 seconds to get some big honking fuel hose like that, like a Formula 1 car, okay? And it's full. There's 40 liters. Yeah, 40 liters from 20 to 60 in an instant. But there's no way this line can be vertical. Okay? Even if it took a millionth of a second, that line is still slanted somewhat. It's not vertical. So this is a function. It does pass the vertical line test. Okay, What's going on? With reference to this journey, explain what is happening between A and B. I already said it. They're driving. They're burning gas. But because this is grade 10, at a constant rate, okay? Exactly 100 kilometers an hour down a flat highway. The wind conditions are exactly the same. It's not headwind, tailwind, okay? All that affects your fuel. Because this is a straight line, we can say it's constant, right? So we are driving at a constant rate, okay? In practice, that's pretty difficult to do, right? Unless you're like a line haul trucker and on one highway, you don't vary your speed. Maybe you're in Saskatchewan, you know, where you can like see Manitoba because it's so flat, right? Seriously, you can see the curvature of the earth. Where are the people who have the most accidents with trains? In Saskatchewan, where you can see a train from 10 miles away. But they're just so, okay, they don't even have to turn their steering wheel on their highways. It boggles your mind. Anyway. Okay, it's not intuitive. Driving at a constant rate. Okay, B and C. Think, this is the fuel. At this time, 10 o'clock, I got 20 liters. At this time, well, that looks like 10:30, right? Halfway between 10 and 11, I still have 20 liters. If you're not burning any gas as time goes on, what do we call that? You're stopped. Okay? You drove for what? 3 hours? Oh, that's enough. Let's have a little break. Okay? Probably pulled into a gas station because we kind of know what happens next. But B and C, you're stopped, right? Half an hour has elapsed. No gas was put in. No gas was burned. The car's off, right? Sure. Brekkie. Brunch. Okay, stopped. How long were they stopped for? Let's get some more details here. From 10 to 10:30, right? So we can add some other extra information here. I know how long you stopped for. We may as well put it in. C and D, we've already talked about it. It goes from 20 liters to 60 liters, according to this, in a very, very short period of time. We know that's impossible, but we're not even going to comment on the time, okay? What happened? What do you call it when the fuel goes up? Fueled up, sure. Filled it with gas, same thing, right? Okay, fueled up. What other detail could we add? Do we know how much fuel went in it? I had 20, now it's at 60, right? That's 40 liters of fuel. How do you know this is in Canada? Or Europe? Yeah, it's in liters, not gallons. Okay, this one's a little trickier. Rate. Anytime you have a rate, it has to do with time, right? How fast something happens. Rate has always got to do with time. What is the rate here? Not the rate of speed in kilometers an hour. I want the rate of fuel consumption in liters per hour between D and E. So I need to know from here to here, how many liters is that? And I need to know the time. Okay, a rate, look at the units. Liters per hour. Liters per hour. That's the same as liters divided by hours, right? Just like, you know, kilometers an hour, that's our familiar one. That's how you write it. Kilometers divided by hours. That's what the odometer on your car shows, right? Speed limit here is 30. 30 what? Kilometers an hour. This is a rate. This is also a rate. So I just need to find out how many liters burned, how long it took, and then just divide them. How many liters from here to here? Well, that is definitely 25. That is 60. What's 60 minus 25? I burned 35 liters. How long did it take? From 10:30 to 2 o'clock. Okay, well, here's how I do this. There's 1 hour, there's 2 hours, there's 3 hours and a half. That's 3.5 hours, right? That's easier than going 10:30, 11:30, 12:30, 1:30, 1:30 to 2 is a half, 3.5, okay? You get the same answer, but let's make it easier on our brains, right? 1, 2, 3 hours, 3.5 hours. Okay, so I burned 35 liters divided by 3.5 hours. I want this as a unit rate. You remember this stuff from grade 8? I don't want a number in the bottom. I want to divide them. Do you know how many times 3.5 goes in 35, Liam? About 10 times. That's 10 liters per 1 hour, or 10 liters an hour. Sounds like a lot, doesn't it? That's what it is. It's a minivan packed with screaming kids and supplies and diapers and full tank of gas. Okay, that's what it is. 10 liters an hour. Which line segment represents the car being refueled for the second time? Where's that, Adam? Where am I fueling it up? Which line looks like C and D? Well, yeah, but they want to know the line segment. That's where it happens. So how am I going to call it? I'm going to call it GH, right? That's the line segment where I fuel up for the second time. GH or HG, whatever, it's the same thing, right? There's no left or right here, top or bottom. Calculate the total time the car is being driven. Okay. Clean this up a bit. Total time it's being driven. Are we including the time it's being stopped? It's a little ambiguous, isn't it? Do they want the total time of the journey? Well, that would be 5 minus, 7 o'clock in the morning. That's 5 hours from here to here. That's 10-hour journey, but not all that time I was driving. So you got a couple choices. You remember this old question with area? And you could take the whole area and subtract that one, or you could take this area and add that one. It's kind of like you have the same choice here. You want to take the total time and subtract the time I'm not driving, or you want to add up this time, and this time, and this time, and this time. Either way should get you the right answer. Yeah, what's the time that's elapsed from here to here? Not even. You can't tell, so you're going to say no time. Negligible. When we're talking 10 hours, what's a minute? We're going to ignore that, right? Yeah. Okay? Okay, right? So, which way? Doesn't matter. Let's look at it this way. From 7 to 10, that's 3 hours. From 10:30 to 2, did I already get this time? Yes, I did. That's 3.5 hours. This is from 1500 to 1600. That's 3 to 4. That's 1 hour. Okay, and finally, there's another hour. So 3 hours, 3.5 is 6.5, 7.5. That's 8.5 hours of driving. Okay, that's one way. Just add up all the times. What's the other way? This was a total of 10 hours. I'm going to subtract this hour, so that's 9. I'm going to subtract that half an hour. Do I also get 8.5? Nice. Okay, we're talking about gasoline here, not the other type of gas. All right, 8.5 hours either way. Okay? That's how long we're driving the car, not stop for. E, let's not worry about that, okay? Okay, if you want to do that, 72, 25. You know what? If someone now put 85 cents a liter, it'd be a lineup for blocks and blocks and blocks, right? Gas is about $1.20. You know, when it's funny, time changes. When I was a boy, seriously, it was $39.9 for like years. And then it went to $49 and people were like, forget, I'm selling my car. That's ridiculous. Then it went to $69 like overnight. Everyone was freaking out. When I looked at this a few years ago, I went, holy cow, yeah, that's getting expensive. Now it's a bargain. In a few years, it'll be like $2.50. It'll be like Europe, $4 a liter. That's why they all drive tiny little Fiats about this big. They get like 80 miles to the gallon. Mark my words. Anyway, okay. Speed versus time. Suggest a possible scenario. This should be an easy mark. If you're kind of creative, it will be an easy mark. And if you're not, well, you got to try to memorize it. What's a possible situation for something that does speed versus time? Car driving, first thing comes into my mind. What else could it be? Could be riding a bicycle. Could be running. Can you walk at a certain speed and then change that speed and go slower and then go somewhere in between? Sure, why not? And then guess what happens here? This is speed. Right at the bottom, we're going to assume that's speed 0. What's another word to say your speed is 0? Stopped. Right? Okay. Possible scenario, a car. Right? We started, so this, we didn't start at 0. According to this graph, we were already traveling. There's no numbers here. I don't know what it is. I don't know. Call it 40 kilometers an hour. We were going 40, then someone started the stopwatch, right? This thing didn't start at 0, like in your driveway. Okay? And then it slowed down. The rate of speed changed over time. We call that acceleration. In this case, it's deceleration. Negative acceleration. You done this in science yet? Yeah. Oh, cool. Deceleration, right? The speed changed over time. Here the speed is constant again. When speed's constant, what's the acceleration? Yeah. Right? Because the rate of speed doesn't change. And if you're taking science next semester, well, try to pay attention. Right? If I increase my speed from here, let's say that's 20, up to here, let's say that's 30, I must have accelerated the car, right? Positive, or just call it acceleration if you're using the word deceleration, right? Okay, and then I decelerated, I slowed down at a constant rate and came to a stop. Okay? In real life, it's pretty hard to decelerate at a constant rate. Either it'll curve like that, or maybe it'll curve like that. You don't get this in Science 10. You don't even get this in physics. Do you know what it's called when you have a changing acceleration? Anybody know the term? You're going to look at it and go, what? If acceleration changes, I'm serious. Okay? You don't even do that in university. I know that because I got a physics degree. You don't even do that in university. But that's what it's called. Okay? It gets really, really complicated when you start doing that. Okay. This is a weird one. Don't yell it out if you see something. I know you're thinking teeth. Okay? It's not teeth. It's speed versus time. It's not your lower molars. What would start at 0 for speed, go up to some value, then go back down to 0, and then do it again, and do it again, like periodic motion? Any ideas? Sorry, Alicia? A bun? A bun? A bunny? You're thinking distance versus time. I know you're looking at this going, okay, he's hopping up, he's hopping up, he's hopping. Yeah. This is the speed. Okay, so it goes up to some value, I don't know, 3, then back down to 0. This is what it is. Think about it, right? Right here, it stops. The speed is 0. At the bottom, it's going fastest. The speed is maximized. It gets up to here and it's 0 again. That's called, what do you call this thing? It's a pendulum. Think a grandfather clock. Okay? There's other examples, but that's the first one. Okay? It's kind of weird, right? Pendulum. All right. We should have an example here with distance and time, so let's throw one in. I already explained it a bit in the other one. Okay, so distance, time, what's going on? Okay, in number 1, this example, I start at 0 for distance. As time goes on, for number 1, what happens with my distance? It increases. It gets to some value. What does that mean? If time goes on, my distance is increasing. Let's say this is my driveway. I'm going to take my driveway at my house at distance 0. I drive, I don't know, 100 meters away. Okay, it took a couple of minutes of time. I must be, what? Doing some speed. Yeah. Okay, moving, doing some speed, right? Okay, so this is velocity, or if I don't know the direction, speed, right? If the distance increases as time goes on, that means I must be moving, right? Velocity or speed. What happens at section 2? What's the definition for as time goes on? Okay, this is it. This is my distance 0 for me right now. Time's going on. How's my distance changing? I'm going to say that way's positive distance, right? Am I going anywhere? No, right? As time goes on, my distance, whatever it is, stays constant. That means I am, what's the word, Calvin? Stopped, right? Okay. And 3, this is again speed. It's again motion. Does this one look, I don't know what your example looks like, but to me, that one looks less sloped. So what can we say about our speed compared with number 1? Yeah, slower, right? Because it's not as steep. If this thing was really, really, really steep like that, see how much distance changes in a short period of time? That means you're going really fast, right? If this thing's like this, my distance doesn't change that much over a longer period of time. This would be like the tortoise, that would be like the hare, okay? 4, so I went a bit further, speed, right? Slower than the first one. 4, is this a horizontal line? It stopped. Okay, I'm not even going to use the word slope here, but I am stopped yet again. And finally 5. Let's think about this in terms of our units. This is distance. Where did I start this journey? In my driveway. That was distance 0. I went further and further away from my driveway. Okay? I don't know what the number is, but then I'm right back where I started, aren't I? Yeah. I went backwards. I had speed, right? But in the opposite direction. Okay? So I'm just going to say end up Back where I started. Yep. I'm not going to go there because this isn't science. Yeah, so no, I know what you're saying. It's totally different too, right? All right, I just want to talk distance here. I'm back where I started. My displacement, that's the vector of distance, is 0, okay? So speed, I had to go backwards. So I started here. This is this graph, okay? 1, I'm doing this. 2, I stopped. I'm some distance away from where I started. 3, I'm going to go again, but this one's going to be a little bit slower. And then this is number 4. I'm stopped again. And then 5 means I'm going some speed, but now I'm right back where I started, okay? Other direction, opposite direction. You can call that a negative speed. Don't worry, we'll get there when we get to slope, okay? All right, so quickly, how about baking a pie? Think you could graph this? What happens? How do you bake a pie? Anyone know what temperature you bake pies at? 425? 350? 325 for a turkey? Okay, I don't know. 350, 325, sure. But this is the oven temperature. This is time. Is your oven already at 350? Don't draw this. It's not, is it? You got to heat it up, don't you? You got to turn it on. Does it make sense to go from here? Don't draw this. Does that make sense? It warms up to 350, and then I bake my pie. Ding, right? Put my pie in. Why doesn't that make sense? Is your house at 0 degrees? It might be. But yeah, what's our house at normally? What's like room temperature? Yeah, so we don't want to start there. We maybe want to start it like at about 20, right? That's what your oven's at. Then we warm it up. We're going to assume that's constant, but maybe it's not. Maybe it's curved a bit. I don't know, okay? Just draw a straight line. We get to 350. Ding, the bell goes, okay? Hey, that means it's at 350. Then we put our pie in, and we bake it for a certain period of time, and then when it's done, well, your oven's going to cool back down to 20 degrees, right? Might not be the same rate as how it warmed up. It probably warms up a lot quicker than it cools down, right? Yeah. So this line shouldn't be that steep. Should be a lot more gradual, but I'm running out of space here, okay? Okay, how about someone running a 100-meter sprint? Does he start at a speed of 0? Yeah. What happens? Do you keep going faster and faster and faster over those 100 meters? So it doesn't look like that, right? What happens? You get up to some certain speed. Do you think you hold that speed till you're done? Or does it maybe dip down a bit? Maybe you tire out? What do you think? Yeah, the 100 meters isn't that long though, right? And if he's doing this thing, he probably like knows how to do it. He probably is a decent runner, because I'm not, so I wouldn't do it, right? I think you kind of get up to some certain speed, whatever that is, and then you continue that until you're done the 100-meter sprint, and then, yeah, you cool down, right? You don't come to a full stop and hit a brick wall, right? You don't do this, right? You gradually kind of, that's probably curved, and then eventually you're going to come to a stop, right? Does that make sense? Okay. And if he does that in about 9.7 seconds, then he's got the Guinness Book of World Records. He can buy all the Ferraris he wants. You know how much runners make? Huge. Right? It's all endorsements and contracts. Okay. That's it. Time for quiz. One thing I want to say, you're going to need this for the first question. Okay, 1 to 3, 5 to 9. Do you know the formula for speed? It's distance divided by time. So, okay, this is the distance for line 1. It got to 4 kilometers, right? Here's line 1. That's how far it went. That's the distance. How long did it take? You got to look here. It starts here. It goes to here. That's 40 minutes, but we don't want it in kilometers per minute. How many hours is 40 minutes? 2/3 of an hour, right? There's 60 minutes in an hour, 20, 40, 2/3 of it. Using this formula, speed is distance 4 divided by time, 2/3. Do you ever want to divide fractions? No. You want to flip it and you want to multiply it. What's 12 divided by 2? 6 kilometers per hour. Okay? That's what they're doing. Which student is this? Well, you got to read the information and try to figure it out. Okay? Okay, x and y intercepts. Should take you, hopefully, 2 minutes. Stop.